For many people, indeed perhaps the majority, the image that they have of the nuclear power industry is of a constant and barely contained threat to human life and health. And Chernobyl has undoubtedly reinforced that view. But is it a valid image? The nuclear power industry, it seems, lives eternally in the shadow of Hiroshima. In no other technology is scientific fact so powerfully blurred by the emotional overburden of the bomb. In these two programs, we shall be going back to square one to examine the basis of nuclear power, the nature of the radiation that it creates, and the threat that it poses, both in normal operation and in the event of an accident. Now, there is a widely held belief that we are, in a sense, still on the threshold of the nuclear age, that it would be a relatively simple matter to switch nuclear power off.
In fact, it's now over 30 years since nuclear electricity first flowed into people's houses in Russia, Great Britain and America. And by 1960, the number of commercial reactors had grown to 17. Over the next 15 years, the number of reactors around the world grew by more than 500%, from 90 in 1970 to 255 in 1980. And there are now over 370 reactors in 26 different countries. The early nuclear experiments bred an extraordinary hope, a belief that scientists had somehow fashioned a magic key that could unlock a bottomless treasure chest of cheap energy. Scientists imagined people would live in spacious underground apartments with rooms and swimming pools heated by private nuclear reactors. Cars and buses would run on nuclear engines, and huge supersonic airliners would be powered by streams of radioactive particles and be able to cross the Atlantic between lunch and dinner. And they even envisaged a terrifying weapon that could destroy the world.
Before dawn on the 16th of July, 1945, at Alamogordo, New Mexico, an event took place which was to change the world for all time to come.
But the tide of propaganda gathered pace throughout the 40s and 50s in an attempt to blot out the memory of the bomb and persuade the American people that the atom was a force for good. It was hailed as the answer to a dream as old as man himself, a giant of limitless power, power to light homes and cities across the American homeland.
The atomic energy power plant has already proved feasible. The future supplying of electric power to entire cities is far from impossible, while nuclear power in locomotives, submarines, ships, and even very large airplanes may all but revolutionize future transportation on land, sea, and air.
But over the first 30 years or so of the atomic age, few of those dreams have been realized. The nearest the world got to an atomic airliner was the testing of a small reactor carried inside the fuselage of a bomber. No one could solve the safety problems. It would lay down, for example, a trail of radioactive waste, and what would happen to the reactor if the plane crashed. As for the passengers, well, they would probably have to be banished to the wingtips to protect them from the radiation. A nuclear ship did actually get launched. It was unquestionably the world's most expensive merchant ship. It cost $30 million and took 5 years to design and construct. It was called the Savannah. The dock workers around the world refused to handle what they described as a floating atomic bomb. As for the atomic car, well, the Ford Motor Company toyed with the idea of a model neatly labelled the Nucleon, but very rapidly this project died a death. However, these practical setbacks scarcely stemmed the flow of pro-nuclear ballyhoo.
Truly, the superpower which man has released from within the atom's heart is not one, but many giants. One is the warrior, another is the engineer, another is the farmer, still another is the healer, and the last is the research worker working in the fields of pure science to reveal more of the mysteries of the universe. But all are within man's power, subject to his command. On man's wisdom, on his firmness in the use of that power, depends now the future of his children and his children's children in the new world of the atomic age.
But let's go back to basics. Everything in the universe is made of collections of atoms. These are the basic building blocks. No one has ever seen an atom, but they're visualized by scientists as very small, slightly fuzzy spheres. Now, at the very center of each sphere, occupying perhaps 100 millionth of its volume, is an even smaller particle, the nucleus. And it's responsible for all the strange phenomena of nuclear physics, from radioactivity to the chain reaction. Now, the nucleus itself is also made up of different particles. The simplest atoms have only a few particles. Hydrogen, for example, has 1, and helium has 4. The key point is that every substance in the universe has a nucleus that's made up of 2 types of particles, called protons and neutrons. Nearly all the properties that we associate with different substances, such as hardness or lightness, or colour or taste, come simply from the different numbers of particles in the nucleus. Each different type of atom is known as an element, and these simple numerical differences in the number of protons and neutrons can lead to very dramatic effects. Now, one of them is that as the nuclei get heavier, some elements, particularly uranium for example, become unstable. It's as if they're unable to settle down with the jostling mass of 235 protons and neutrons that are crammed into the nucleus. Every now and then, one atom will behave oddly. It will throw off a clump of 4 particles, which are known together as an alpha particle, and it also emits a burst of gamma radiation. This property we call radioactivity, and it produces radiation. There are 4 different kinds of radiation. Alpha particles are quite heavy on the nuclear scale, but they only travel a few centimeters in air. They can't penetrate the skin, and they can be stopped by even a sheet of paper. But if you breathe in an alpha-emitting substance, these heavy particles can do a tremendous amount of damage to the cells they plough through. Beta particles, however, pose a threat both inside and outside the body. They're much smaller and travelling at much higher speeds. They can easily rip through the skin. However, they can be stopped by a few millimetres of plastic, or a sheet of glass, and even by a layer of water. The 2 other forms of radiation, gamma rays and neutrons, are by far the most difficult to shield against. Gamma radiation comes in the form of rays, rather like X-rays, while neutrons are heavy particles with enormous energy. They can both penetrate most substances, including the human body, causing immense damage to cells as they do so. To stop them, you need several centimetres of lead, at least 1.5 meters of special glass, as in these remote handling cells at Harwell, or several meters of solid concrete, which make up, for example, the biological shield that's wrapped around every nuclear core. But the fundamental point is that with the exception of neutrons, all these forms of radiation exist not only in the laboratory and the power station, they're all around us, as part of the natural environment. The basic problem, of course, as it's so often been said, is that we can't see or feel or taste or smell radiation. One of the reasons, perhaps, why it arouses so many fears. But that we are all constantly subjected to natural background radiation is unquestioned. Here in Somerset, for example, I'm getting about the average dose for the nation as a whole, rather more in Cornwall, rather less in parts of East Anglia. And to put a figure on that, one estimate is it amounts to 15,000 particles a second striking the body every second of every day, coming from the rocks and soil and cosmic rays from outer space, nothing at all to do with nuclear power. In the UK, for example, as in most other parts of the world, about 80% of all the radiation we're exposed to comes from these natural sources, as opposed to less than 1% that comes from the nuclear power industry. But the natural background level varies widely across the country. In general, the darker the shading on the map, the higher the average background radiation. But there are several hotspots where the background levels are several times higher than, say, in the southeast. These are the largely granite areas of Devon and Cornwall, Wales, Yorkshire and eastern Scotland. The radiation cloud from Chernobyl deposited a worrying but nonetheless relatively small addition to the total background radiation experienced for the year as a whole. However, they're still assessing the long-term effects of radionuclides taken up by plants. This is an old, disused mine in Cornwall. They used to mine copper here, but in these rocks there are clear indications that we live
on a radioactive planet, and indeed always have done. When the Earth was cooling all those millions of years ago, a few of the elements that make up the rocks of this planet came to have atoms with the unusual quality of splitting spontaneously, what we now call radioactivity. One of them is uranium, and in these rocks there are seams of uranite or uranium ore. You can hear some of the radioactivity being given off by these small deposits.
What's happening at the atomic level is that the nucleus of the uranium atom releases a cluster of particles and a burst of gamma radiation. It's been going on, as I said, since the beginning of time. But only in the last 100 years or so have we been able to measure it and become aware of the damage it might cause.
One of the effects of the increasing concern about radioactivity has been the development of more and more accurate ways of measuring radiation, and that in some cases has led to greater concern. Because as the scientists have continued to explore both the sources of radiation and its effects, they've come up with one or two surprising results. One of them, for example, is the hazard represented by the naturally occurring radioactive gas called radon that collects in our houses. This old Victorian stone house in Cornwall was taken over some 18 months ago by the National Radiological Protection Board, the NRPB, as part of a study into ways of reducing the build-up of radon gas in houses. They measured levels in 2,000 houses, and the results indicate that across the country, in as many as 100,000 homes, people are getting the same sort of exposure as allowed to nuclear power station workers. And in many homes, perhaps as many as 1,000, they're getting 5 to 10 times the exposure of nuclear power station workers. And that's one of the reasons why radon gas has become a major focus of international concern. Because for most of us, radon gas is now the biggest single source of radiation exposure, apart from the occasional X-ray. And paradoxically, the situation is made far worse by the modern passion for double glazing and draft proofing. In a well-ventilated, that is to say, a normally drafty house, most of the radon gas leaks away. But where it's trapped, by double glazed windows, for example, or sealed doors, it decays into other substances known as radon daughters. They're particles, they can get trapped in the lung, and they can cause lung cancer. Indeed, it's shown they can cause as many as 5 to 10% of all lung cancers. And we can demonstrate how that works. What we've got here is an alpha counter because radon and radon daughters give off alpha radiation, the kind that's most damaging to human tissue, and a kind of mechanical lung, sucking the air in the house through a white paper filter, which is acting rather like your bronchial tubes, collecting particles of radon daughters. Now, if I expose the alpha counter to the air in the house, there's no reaction because the concentration of radon daughters is too low. If I now test the filter, i.e. your bronchial tubes, you can hear there how many particles are collected in just half an hour, the time we've been running the mechanical lung. Now, compared with radon gas, most other sources of natural background radiation really pale into insignificance. But there are some. For example, even the food we eat can be radioactive. Brazil nuts are rich in fats and protein and good for us in all sorts of ways. But they're also mildly radioactive. They contain radium and thorium, both alpha emitters. Many mineral waters have higher than average concentrations of radon gas, again an alpha emitter. One of the vital elements we all absorb from our food is potassium, but one form of potassium, K40, is also radioactive. We all carry some K40 in our bodies all our lifetimes, bombarding us from the inside with 200 or 300 particles a minute. Now, why am I going on about this? Why am I going on about radioactivity in our houses, radioactivity in our food and so on? Well, certainly not to alarm you, but there are 2 or 3 important points to be made. One is that scientists agree that nature is the biggest source of radiation for all of us. Concorde pilots, for example, are essentially radiation workers. They carry exposure meters on their lapels because of the higher than average doses of cosmic radiation they receive during their high-level flights. The second point is there is no real difference between all these sources of radiation: nuclear power station emissions, medical X-rays, and the radioactivity in our food and so on. They're all the same. But most important of all, if the cells in our bodies were to shrivel up and die when they were hit by, say, a beta particle or a gamma ray, there wouldn't be many of us left around. The fact of the matter is that because we have evolved on a radioactive planet, we've developed repair mechanisms that can make good most or all of the damage we incur from the radioactivity in our food or the radon gas in our houses.
Now, the problem is that most of us misunderstand the hazards of radiation. Very difficult for us to separate out the harmless from the worrying. When, for example, we asked a sample of the British public a few weeks ago about their understanding of the hazards of radiation, one of the questions we asked was, how near can you safely be to the following substances?
A piece of granite.
To touch it.
A lump of uranium ore.
Could not touch.
About an ounce of plutonium.
Could not touch.
But could you be in the same room as it, do you think?
No.
A fuel rod before it goes into a nuclear reactor.
Could touch.
The fuel rod after it's been used in a power station. I suppose you could really be in the same room as that, but not touch it.
In that survey, we listed 5 items: a piece of granite, a piece of uranium ore, an unused fuel rod, a piece of plutonium, sometimes called the most dangerous material on Earth, and a used fuel rod. We asked people to choose whether they could touch the substance, be in the same room as it, or whether they would have to be behind some sort of protective shielding. Let's look at the results we got for the first material, granite. 88% of the people questioned, that's roughly 9 out of 10, saw no problem with holding granite. They were right, although there were 1 or 2 doubters. The official answer, well, that has them all in the same room holding the granite. Well, as you might expect, most people saw no problem with granite, although 12% thought you had to take some care. It is, of course, one of the commonest rocks in these islands, the Scottish Highlands, Dartmoor and all that. It is lightly radioactive. I can, for example, get a reading on this Geiger counter. There you can hear the radioactive emissions, and it is involved in the creation of radon gas, so a slight radioactive problem with granite. Let's move on now to uranium ore. 22% of the people questioned thought that you could safely hold uranium in the hand. A further 22% saw no problem about being in the same room as the stuff, but 49% saw a need for some sort of protection from it. In fact, the official answer is that you're not likely to come to any harm holding uranium. This, of course, is what a lot of the fuss is about, the basic raw material of the nuclear power industry. Much more radioactive, of course, than granite. You can hear there the fierceness of the Geiger counter's response, but still quite safe to handle, otherwise I wouldn't be handling it. Now, the uranium metal is refined from the ore and goes to make up the fuel rods that go into many of Britain's nuclear reactors. How close can you get to those? Well, almost 2 out of 10 people believe that you could hang on to them. Another 2 saw no problem in being in the same room, but most people, 56% in fact, only felt happy with a wall between them and the uranium fuel rod. The official answer, surprise, surprise, is that you can safely hold these rods. So over half the people surveyed thought you couldn't get near one of these. In fact, as you see, you can. Although, let me emphasise, it is an unused fuel rod, hasn't been anywhere near a reactor core. Something like 50,000 of these would go to make up a typical reactor core. In some ways, safer to handle than the uranium ore itself because it's encased in this magnesium alloy cladding, what they call a fuel can. OK, that's a fuel rod. Let's move on now to the element plutonium. Plutonium is a word so bound up with a bomb that understandably perhaps only 16% thought you could safely be anywhere near the material. Almost 8 out of 10 people wanted to have nothing to do with it. Now, the official answer, to most people's surprise, is that you can safely, if not happily, be in the same room. However, it is standard laboratory practice to keep it isolated from the air. Well, we've got some plutonium inside this double-skinned plastic bag. Plutonium has really had a very bad press down the years. It's been variously described as the most deadly or the most toxic substance on Earth. But if toxic means poisonous, there are many other chemicals far more poisonous than plutonium, things like arsenic and cyanide and so on. It's also thought to be such a powerful emitter of radiation, you have to stand a long way away from it. Well, that obviously isn't the case, otherwise I wouldn't be as close as this to it. But let's not minimise the dangers of plutonium. Its real dangers lie in the fact that it's a powerful emitter of alpha radiation that can be contained safely by this double-skinned plastic bag. But if a particle were to lodge in the lungs, then the heavy alpha particles could cause a great deal of damage. It's also active for a very long time indeed, well over 200,000 years. So it goes on causing damage for that sort of period of time. It's the stuff of bombs
and weapons, of course. So every milligram of plutonium has its own docket. It has to be accounted for wherever it goes. So that's plutonium, not quite perhaps as fearsome a material as its reputation would have us believe. But what about the last of the items on our list, the used fuel rod? Well, that's 20 feet down at the bottom of this cooling pond.
As for the general public's response to the idea of being adjacent to one of them, well, almost 9 out of 10 people wanted to be behind some form of protection. And indeed, the official answer in this case is to stay well away, because used fuel rods are perhaps the most potent concentration of radioactive materials on Earth.